You know, there's this weird, unwritten rule that seems to run through the entire history of science. Every single time there's a huge leap forward, it's first met with a wall of resistance, ridicule, or even outright suppression. It's a pattern we've seen again and again. So, the big question is, are we making the same mistakes right now?
And look, this isn't just a fluke. It's a recurring theme. The path to a new scientific truth is almost never a smooth ride. It's more like a battle against the established way of thinking, where these revolutionary new ideas are treated like heresy at first, only to later become the new common sense.
So, to really get a handle on how this all works today, we first have to take a step back in time. Because the history books are just filled with stories of brilliant people who were silenced, ignored, or punished just for being right a little too early.
What's really wild is how consistent the backlash has been. I mean, you go from Anaxagoras being exiled just for suggesting the sun was a flaming rock, not a god, to Aristarchus being totally ignored for proposing the earth went around the sun, all the way to Galileo getting put under house arrest for actually proving it. The common thread? All of their ideas rocked the boat and challenged what the powerful believed to be true.
Okay, so as science gets more professional, the pushback evolves. It's less about heresy trials and more about rejection from your own peers. You've got Ignaz Semmelweis, who is mocked for the incredibly simple idea that doctors should wash their hands. Alfred Wegener's theory of continental drift was laughed at for 50 years. Even the great Subramanian Chandrasekhar had his groundbreaking work on black holes dismissed in public by a top astronomer. The resistance just became part of the institution itself.
Right, so how does this pattern play out today? I mean, we're not putting scientists on trial anymore, but that doesn't mean the forces holding things back have disappeared. They've just gotten, well, a lot more subtle.
See, today, the suppression is kind of baked into the system. If you have a truly radical new idea, it's going to struggle to get funding because it's seen as too risky. Then it faces a mountain of skepticism during peer review. The very system meant to ensure quality can also act as a gatekeeper. And hey, even if it gets published, academic search algorithms can basically bury it because they're designed to promote papers that are already popular. It's this vicious cycle that rewards tiny, safe steps instead of the huge, game-changing leaps.
And this all leads to a really critical, maybe even a little scary question. With all of these subtle but powerful systems in place, could we be ignoring the next Copernicus or Wegener right now? To see this in action, let's look at one of the biggest, most fundamental fields there is: cosmology.
All right, so for the last few decades, our main guide to understanding the universe has been the standard model of cosmology, or Lambda CDM, and it's been amazingly successful. But lately, some pretty serious cracks have started showing up in that foundation.
So, on the one hand, Lambda CDM is brilliant. It perfectly describes the afterglow of the Big Bang, and it nails how galaxies clump together. But on the other hand, it has some huge problems. We're seeing major disagreements on how fast the universe is actually expanding. And here's the real kicker. Its two main ingredients, dark matter and dark energy, which is supposed to make up a whopping 95% of everything, well, we have absolutely no idea what they are. These aren't just little loose threads. They suggest we might be missing something fundamental.
So whenever a big, established theory starts to wobble, that's when new ideas have a chance to pop up. And one of those ideas, from an independent researcher named Hakan Üçok, suggests a completely different way of looking at the entire cosmos.
Instead of just trying to patch the old model with more mysterious particles, the S-matter framework does something way more radical. It suggests that our whole four-dimensional universe is basically a projection from a higher, five-dimensional reality. In this picture, what we call dark matter isn't a particle at all. It's just the gravitational shadow of matter from that fifth dimension. And dark energy isn't some weird force. It's a cosmic inflow of energy from that reservoir that's stretching our universe. It's a total rethink.
Okay, but look, a wild idea is just a wild idea, right? Unless it makes specific predictions we can actually go out and test. And this is where the S-matter framework starts to get really, really interesting.
Remember that Hubble tension we talked about? That big crisis for the standard model? Well, guess what? The S-matter framework actually predicts it. It says the huge empty voids in space should be expanding faster than the dense, clumpy parts. It's incredible. What looks like a massive, universe-breaking problem for one theory is just expected behavior in this new one. Here's another one. The standard model says dark energy is a constant. It never changes. But this framework predicts it should be evolving, maybe even getting stronger over time. And what's just wild is that the very latest data from a huge project called DESI is starting to show hints of exactly that,
a pretty significant deviation from the constant model, just like sad matter says.
Okay, but this next one might be the boldest prediction of all, and it's super specific, which means it's super testable. It calculates that about 616 new hydrogen atoms are constantly being created in every cubic kilometer of empty space every 1,000 years. I know, that sounds like almost nothing. But the implication is huge. It means there should be brand new, pristine hydrogen clouds popping into existence out in the deep voids of space, right where we'd expect to see absolutely nothing.
So let's just pull back for a second and look at the big picture here. The whole point is that the S-matter framework tries to solve all these different cosmic puzzles: dark matter, dark energy, the Hubble tension, even the Big Bang singularity, with a single unifying idea. Instead of needing a separate patch for each problem, it's trying to build a whole new foundation.
Now, it is so important to say, this is just a proposal. This isn't some new gospel we're supposed to just accept. That's not how science works. The whole point is that every idea, no matter how cool it sounds, has to be put through the ringer and tested.
And believe me, the tests are on their way. Future data from DESI will give us a much clearer picture of dark energy. The Euclid Space Telescope is going to hunt for those strange gravitational effects in cosmic voids. And our most powerful radio telescopes are going to search for those 616 hydrogen atoms. The bottom line is, this theory is going to live or die by the data. There's nowhere to hide.
And that really brings us to this powerful idea. It's a reminder that science isn't about having a book of unchangeable facts. It's a living, breathing process of getting less wrong over time, of being willing to let go of old ideas when the evidence points somewhere new.
And that brings us right back to where we started. From Galileo to Wegener, history has one very clear lesson for us. Real progress happens when we judge new ideas by the predictions they make and the evidence they gather, not by who came up with them or how comfortable they make us feel. Whether the S-matter framework turns out to be right or wrong, the only way forward is to let the data have the final say. That right there is how science takes its next great leap.